Welcome to Learning to Engineer. Today we will see the concepts of second order systems with the help of some problems which are taken from GATE exam. These are the formulas and information that we need to remember in order to solve these problems. There are derivations for them. You can find them in books and several other channels. The detailed derivation of the response is not required with respect to your exams. Hence, they are not covered in this video. We are just going to look at key concepts and use them to solve some problems. Let's get started. If the characteristic equation of a closed loop system is s square plus 2s plus 2 equal to 0, then the system is dash. Is it overdamped, critically damped, underdamped or undamped? We need to find out the damping ratio in order to answer this question. The damping ratio is just the ratio of the actual damping alpha divided by the natural frequency. In a pole zero plot, we will be able to find them easily. Let's say you have a pole here. The horizontal distance represents the alpha and the vertical distance represents the omega. Okay, and this is the natural frequency of oscillations. Okay, so let's find out delta with the help of the characteristic equation that's given to us. In a characteristic equation, this term refers to the omega n square and this term refers to 2 delta into omega n. So, what is omega n? Omega n will be the square root of 2 radian per second. Therefore, by comparing the coefficients, we can find out the value of delta. Delta is equal to 2 divided by 2 into root 2, which is 0.707. This is less than 1. Therefore, this is an underdamped system. The correct answer is option C. If we have delta to be greater than 1, it is overdamped. If it is equal to 1, this is critically damped. If it is less than 1, it is underdamped. And if it is 0, it is undamped. We will look at one problem to know how the response will be with respect to the damping ratio delta. A second order system has the transfer function 4 by s square plus 4s plus 4. With r of t as the unit step function, the response c of t of the system is represented by dash. 4 responses are given to us. In the first one, we have one peak overshoot and the system eventually settles at 1. Next, we have a response which directly reaches the final state from 0. There is no overshoot at all. In the third one, we have a response that has oscillatory movement. It doesn't settle at all. And in the fourth one, we have a similar response as of V. We will find out the value of natural frequency of oscillations and damping ratio by comparing the coefficients in this characteristic equation. The natural frequency of oscillation is the square root of 4, which is 2 radian per second. So, therefore, 2 del omega n is 4 by comparing the coefficients. So, what is the damping ratio? 4 divided by 2 into omega n, which is 4 by 2 into 2, which is 1. So, this is a critically damped system. What happens to the overshoot? For a critically damped system, when we substitute the value of delta to be 1, we don't have any overshoot at all. So, this behavior happens in 2 of the options. It could be option B or it could be option D because both of them do not have any overshoot. When delta is 0, the system has an oscillatory behavior because the C of t will have a sine term in it. So, when delta is 0, there is no damping at all offered by the system, hence the system does not settle. Let's find out which one. Is it either option B or option D? That's correct. When we examine these graphs, the settling time varies for both these options. The option B settles at 2 seconds and the option C settles after 5 seconds. So let's find out the settling time Ts for 2% tolerance. Ts is 4 by delta into omega n, which is equal to 4 divided by 1 into 2, which is 2 seconds. This aligns with option B. So option B is the correct answer. Here we have a similar question where group 1 represents 4 transfer functions and group 2 represents their responses. We need to match them based on their response. We have 4 transfer functions P, Q, R and S. Find their delta, their damping ratios, then find out the omega n and hence find out the settling time, and we will easily find that the C infinity or the final value. Once we find out these information, we can find out their responses easily and match. I am leaving this exercise for you. In case you have any difficulty, you can let me know in the comment section. Okay, this is just based on the problems that we solved earlier. So if you want, go rewind this videos, check these 2 problems and you will be able to solve the third one by yourself. Step response of a set of 3 second order underdamped systems all have the same percentage overshoot. Which of the following diagrams represents the poles of these 3 systems? The denominator term in the transfer function talks about the poles and the numerator talks about the zeros. Once we have the transfer function, we plot them as a pole 0 plot similar to the options that you are seeing on the screen. There are 3 second order underdamped systems and they all have the same percentage overshoot. Which of the following represents the poles of these 3 systems? It's given that the system is underdamped, which means delta is less than 1, and it's mentioned that the maximum overshoot is same. So when maximum overshoot is same, it means that the delta or the damping ratio is same for all 3. Okay, so when damping ratio is same, what does it really mean? Let's say we have a pole over here. It is offset by a horizontal distance of alpha, which is the actual damping, and the vertical distance is the frequency of oscillations omega, damped frequency of oscillation. That is, after the damping factor is considered, at what frequency does this response oscillate? That is the damped oscillations. Diagonal distance refers to the natural frequency of oscillations. So let's zoom in over this right angle triangle. This is omega d, this is alpha, and this is omega n. Okay, so what is alpha? Alpha is delta into omega n. So when they say that the delta is same for all 3 systems, it denotes that delta 1 is equal to delta 2 equal to delta 3, which is same as alpha 1 by omega n1, alpha 2 by omega n2, same as alpha 3 by omega n3. So this ratio is said to be the same for all 3 systems 1, 2 and 3. So what is this ratio actually? This is actually the cos of this theta. This angle is theta and the cos theta is alpha by omega n. The cos theta is same for all 3 systems. Now let's examine the option that's given. In the first diagram, all 3 poles have different values of omega n but same values for alpha. So this does not make the cos theta to be same. In the option B, the angles theta differ for each of these poles. So again, the cos theta will not be same for the second option. But for the third All of them lie along the same straight line and the angle is same at each case. So thus the value of cos theta is going to be the same. So option C is the correct answer. In the next question, the transfer function is given. For a unit step input to the system, the approximate settling time for 2% criterion is dash. 4 options are given to us. The easier way to solve this problem is by using dominant pole concept. One at -1 and another one at -100. So this pole does not have much impact to the system. So we are going to consider only one pole that's closest to the imaginary axis. It's given that it is a unit step input. So C of s is 1 by s into 100 by s plus 1. So what is the time constant of the system? It is 1 second. So therefore the settling time will be 4 into 1, which is equal to 4 seconds. In this question, a causal system having the transfer function 1 by s plus 2 is excited with input 10 u of t. The time at which the output reaches 99% of its steady state value is asked. What is a causal system? A system whose response depends on the present and the past inputs is called as a causal system. So indirectly this is a closed loop system. That's what is implied. Okay. So in this closed loop system, the input excitation is 10 into u of t, which is a unit step function. So the R of s is given as 10 by s and the transfer function of the system is h of s, which is 1 by s plus 2. What is the response? The response C of s is equal to R of s multiplied by h of s, which is 10 by s times 1 by s plus 2. So what is asked here? The time at which the output reaches 99% of its steady state value is asked. So let's say C of t1, where t1 is the time taken to reach 99% of steady state value. So this is 0.99 into C infinity. C infinity is the response at steady state or at time t tends to infinity. Let's first find out the final value of this response and let's find out C of t1. Then we will find out t1 as the final step. Okay. So C at time infinity is equal to S into C of S as S tends to 0 from the final value theorem of Laplace transform. So this is equal to S into 10 by S into 1 by S plus 2. So this is going to be 10 by 2, which is 5. The final response is at 5. What is 99% of it? 99% of C of infinity is equal to C at t1, which is equal to 0.99 into 5, which is 4.95. So what is asked? When the response is 4.95, what is the time or how long does it take to reach 99% of the response? That is what is asked. So let's find out the response in time domain. This will be the Laplace inverse of 10 by s into 1 by s plus 2, because this is the s domain response. Let's find that in time domain and then we will use this information to find out t1. So this is 10 from the limit 0 until t e to the power minus 2t dt. So when we calculate, we get this. So 5 into 1 minus e to the power minus 2t is the response in time domain. So when this happens at time t1, this is 5 into 1 minus e to the power minus 2 t1, which is 4.95. That is what we found here. So we can easily calculate to find t1. So 1 minus e to the power minus 2 t1 is equal to 4.95 divided by 5. So this implies that, so when we take logarithm to cancel the exponential term, we get t1 as 2.302 seconds. Go back to the question to find out which option is right. So option C is the correct answer. Thanks for watching. In the next video, we will see how a compensator is designed, and the primary purpose of compensator is to adjust the system response, how quickly we want and how maximum can the overshoot go. Based on all these factors, we design the compensator. We can look at specific problems in this area in our next video. Thanks for watching. If you have any doubts, you can let me know in the comment section. You can also email to learningtoengineer@gmail.com. Thank you.